Great. So with that, let's move on to our second main event of today, which is this talk by Fiona Victoria. She is a student at the University of Washington. And to be honest, one day I'm always looking at papers that happen to be citing flower, because I'm kind of curious what people are doing with it. And then one day I was just browsing through the list on Google Scholar, and I found a really provocative title, at least to me. Had a great name, Phoenix, and it was on a really topical, highly topical domain of diffusion models. So this, of course, the models that are driving things like stability, AI, and a lot of this Gen AI hype, which is really shifting the needle on applications in the space. And we think, at least, when you combine that with federated, some really magical things are possible. And so then I reached out to Fiona. She graciously said she'd be happy to give a talk at Flower Monthly. And so Fiona, thanks for joining us today. I'll stop sharing so you can show us your slides. And I'm really fascinated to hear what you've been working on.
Thanks, Nick. Super excited to be here, and thanks for inviting me to this talk. I think it's truly an exciting time in the age of Gen AI, and I think this topic is aligned to what's going on out there in the world. So I can share my screen. Are you guys able to see my screen?
Yeah, it looks great to me.
Okay. So this was a work that was done during my time as a graduate student at the University of Washington, Bothell, alongside my research advisor, Dr. Afra Mashadi, who's also an active contributor and a collaborator, who's also been in a couple of meetings here with Flower. And the title of my work during this time was Phoenix, which is a federated generative diffusion model. So just before I go into the whole, the work and what I did, I wanted to give a bit of a background to it. So Gen AI, in the context of images, is usually reliant on 3 different models, which are your variational autoencoders, your GAN networks, and diffusion models. You may have heard of these GAN networks being used more often than not. And that is very typically a discriminator and a generator network that kind of fit against each other, and then they try to fool each other till they can generate really good images. However, I wanted to go a little different direction, where diffusion models is something that hasn't been yet thought of in the domain of FL. And so decided to go a little bit deeper in working on that. So diffusion models are probabilistic in nature, and they were actually inspired by physics. And they work in a way that they learn how to create something out of just noise. So that's pretty fascinating, and I can show you in a second as to how they really do that. And if you go a little bit into diffusion models, there are 2 types of it. One is your conditional, and another is conditional models. An unconditional neural network model is essentially one in which you don't really provide any kind of a prompt or a text, and it just generates something out of a random seed value. So you just give it noise, and it's trying to essentially create something out of nothing. But in terms of a conditional diffusion model, you would actually tell it exactly what you wanted to create. So if you gave a prompt of, say, a girl holding a duck, it would actually follow those text prompts and generate an image that is closely resembling the text prompt. So the work that I'm talking about is mostly focusing on diffusion models in an unconditional sense, where I'm just going to provide seed value and ask the model to generate different types of images based on what it was trained on. So diffusion models, like I said, are generative models, and they are probabilistic. They're a very simple 2-step process where you have your forward diffusion model, and you add Gaussian noise in iterative test steps, and you try to noise this image. And during the reverse diffusion process, you employ a neural network model to learn how much of noise is added to these images, and you try to remove them iteratively till you can actually get back the original image. And that's a pretty new process, because an image which was just noise, when you try to denoise it, you don't really get the same image back, but you end up getting variations of images because of the noise that was added to it. And this is the super special process of diffusion models, which is why we're able to create so many variations of image, although it was just trained on a very small subset of samples. So why FL for diffusion models? I think the main reason I picked FL was because it can create high quality samples, and there's ample mode coverage, and they also don't suffer from the instability or conversion issues like GANs, which is a common problem as noted by Google itself. And why diffusion model is because there's a lot of, there's on-device data. And by using FL, you can also promote that there is a lot of privacy and security of both the users and the different data that they're being shared. And this also enables collaboration from multiple institutions. So if you use FL for diffusion models, it is actively can be used by healthcare industry, by the autonomous vehicle industry, and also in factories and environment. So in terms of health, you could use it for applications where you want to generate large amount of anomaly synthetic data where you don't have a lot of real samples. And in case of AV, you could use it for real-time monitoring. And in terms of factory, you could use it to generate a lot of defect items, or you can try to simulate how something would look like in a production line, thereby optimizing it. And in terms of environment, you could use it to generate real-time scenarios of how the world would look like if there was a tsunami or a tornado. So that would be helpful for forecasting climate change. So Phoenix is the model that I trained on a FL setting. And the main use of this model is that it addresses the issue of statistical heterogeneity or class imbalance. So what is statistical heterogeneity is that typically this is a common problem in FL wherein you don't really try, let's say you have a scenario where there are 10 different clients participating in a training. And there are times in which certain clients don't really have all of the classes. And when you try to aggregate them together and you ask the server to generate something, it might have never learned a lot of samples. So it's not going to be really representative during the test time. So this class imbalance is not really an ideal scenario in diffusion models, because if it hasn't seen a lot of classes, it's not really going to generate those classes during test time. So I'm trying to learn how I can address these issues, and then came up with two strategies called the data sharing strategy and the personalization in order to combat this main issue. So the first is the data sharing strategy. So consider a scenario where you have a global model and you have multiple clients which are connected to it. A data sharing strategy works in a three-step process, wherein in the first round, you have a global model, which is trained on a small portion of data that I call my globally shared data, or G. So this is usually just a small segment of data. So consider I'm using a Ciferton data set, which has 40,000 training data. I'm going to isolate a small portion of that and call that my G. And I'm going to train a global model first on its small subset G. Once I have a good model on the small data, I'm going to share the weights of this model to all my different clients, and also share a small segment of this G to all the different clients. So what happens now is that all these clients that might not have all the different classes it needed to have might have learned some of those qualities from the global model. So when you do this, and you do that in iterative steps, you ensure that there is equal representation of all classes. So if you kind of repeat this process over, say, 10 server rounds, 100 server rounds, in the end, the global model is going to be really powerful enough, because it has also learned all the different local data, but also learned how to represent this small portion of G. And this is one way of ensuring that you can, deal with the class imbalance issue. The second is a little interesting, and it was just a idea that we came up with, which is personalization and threshold filtering. So personalization threshold filtering is, again, a three-step process. And in this strategy, the first step we do is you personalize these layers. So FL, typically, we consider that all the clients have the same exact model architecture, and they have the same hyperparameters. But here, decided to personalize some of those layers. So what happens in this case is the last couple of layers, or the last basic blocks of this neural network models, are quite different for different models. So they are pretty adaptive to the local data in these different clients. So once I personalize these layers, I then ask these local devices to generate samples for me, and then I continuously monitor their performance. So what I mean by monitoring performance is by actively asking it to generate me, say, 1,000 random images from the diffusion model, and I'm going to measure the FID score, the IS score, the precision and recall. So this is done actively in order to find out what's the diversity of the images being generated and what is the fidelity of the generated images. Once I keep recording these metrics, I'm going to keep, disconnecting or unregistering the underperforming clients. However, it's not really ideal if you just, disconnect a client just because it did not perform well in one server round, maybe there could have been an issue where it did not have good network, or at that particular server round, it did not have really good samples. So rather than just disconnecting them after the first time itself, I'm employing a two-strike approach where I give a chance and keep monitoring those warned clients, and I just keep looking at them. And the minute I see that they're actively doing it again and again, and they're just not performing really well, I end up disconnecting these underperforming clients. And what happens because of this is that I can maintain the class balance and also make the convergence process much faster. So these poor clients are not really dragging the performance of the overall model down. And I see by doing this process, you can still generate really good samples and still maintain more diversity. And here are some interesting results from the first strategy that I employed, which is data sharing. So I use a DDPM model, which is actually a diffusion model, which is based on the differential, probabilistic in nature. And I use it with a unit backbone, which is the standard neural network architecture used to do the reverse diffusion process. And the two variables, like I mentioned, which are my alpha and beta. The alpha would be my local data, and my beta would be the small segment of global data that I had initially allocated. So by doing these different experiments, it was noted that as I kept increasing the beta, the performance of the precision and recall kept increasing. However, it was noted that it did not really matter how much of local data I shared back to the different clients. Even if I just sent back 20% of it, or even 100%, it wasn't really making a lot of difference. And that you can see in the third graph, because the graph stays pretty flat there. The fourth is a little different, and this was something that we just came up with as to how do we really measure the mode? How do we measure the coverage of the classes? We keep saying that I'm trying to address the issue of class imbalance, but there should be a way that I can actually look at it visually to say, okay, these classes are not being actively covered, and these classes are always being repetitively generated. So for that, we came up with a way wherein I use a pre-trained neural network model called the, we just use one of the state-of-the-art pre-trained models, especially for CIFAR10. And then I feed all my generated images to this model, ask it to tell me what class they might belong to. And then I kind of plot all of them to see the frequency of occurrence. So the red line is kind of the base or the ideal scenario we would want. That is, if you had a CIFAR10 test set of 10K samples, there's usually 1,000 images for every class. That's usually the ideal scenario. However, we see that since we're using an unconditional diffusion model, where we try to generate something out of seed noise, it's not going to be really possible to replicate the same thing, but we're trying to ideally bring it to a flat line. The first, which is the blue line, shows where we have employed no sort of class heterogeneity, nothing to combat it, and that's just a default training. And it shows how certain classes were just queuing the results. So for instance, class 0 had almost 6,000 images, where some of the classes had no images at all. But when we try to employ this data sharing strategy and we improve the beta, we could see that it was trying to at least generate more samples across the board. So that showed that, yes, the model has learned how to equally generate images of all different classes, especially from CIFAR10 dataset. And the next is the personalization and threshold filtering. So like I said, this is a two-strike approach. And I use the last basic block of the unit model as my personalization. The results are pretty good, and they are much better than that of a default training. However, the precision and recall did not beat that of the data sharing strategy. The main reason was because we are using something called the filtering, and we end up disconnecting or unregistering some of the clients that don't perform well. There are chances that these clients may have had the only classes that no other client ever had. So by taking that certain client off, you might not let it participate in certain rounds, and thereby the final global model might have not learned certain classes ever during the whole training. So that's one of the reasons why the performance is not as great as that of the previous method. But it was certainly interesting trying to experiment with this method as well. And the graph is quite similar to the last one, where you could see it was trying to flatten the curve, but not as much as that of the previous method. And I guess putting it all together, we could say that the Phoenix does outperform the default training. But if you compare the two different methods that were put in place, the data sharing strategy significantly performed. By just sharing 4 to 5% of the global data, we could show that there was ample performance boost across the board for precision, recall, and interception score. And the best thing about using DDPM was that it was a very stable training. Unlike GAN models, we wouldn't have to actively look at the training and learn when to stop it, because it's not going to start behaving unstable or fluctuate in training. So that was a good thing as well. However, the things to note here is that it's highly, computationally expensive. DDPM models have almost 35 million parameters, which is 6 times that of a GAN model. So since there are 6 times that many million parameters, we're going to have the same number of hours, extra hours to train them. So that took along, 11 to 12 hours per server round, which is not ideal in at least an FL sense. And these are just some of the generated samples that you would see using a default diffusion model where you don't really take care of the class imbalance. And you can see in data sharing strategy, you have much better images with high fidelity. And the personalization is quite comical in nature in terms of the images generated. And it's not, really beating that of the data sharing strategy. So here are some of the open source contributions I think might be really good and beneficial to the community as well. So one thing that I plan on doing is trying to come up with a way where you can limit the number of clients per round of training. So this was something that as an individual contributor I faced, because sometimes we just are having very limited amount of memory size of GPUs, but we want a lot of clients to train. Say you want to train with 100 clients, but you really can't train all 100 clients at once because your GPU just doesn't have the capacity to do it. So I had to tweak the code to limit the number of clients and kind of go in a round robin fashion so that all of them get the chance to participate in the upcoming server rounds. That's not ideal, but I think it's really good, at least in a simulation sense, to get started with it. And another thing that I wanted to use was trying to drop clients based on performance. Although Flower doesn't have a way into it to directly unregister or drop clients, it was pretty interesting that they do have those procedural calls or the functionality to do it. It just hasn't been integrated as a whole strategy yet. So I made use of those existing function calls out there to unregister or drop clients and also track the historical performance of these clients. And I think having this functionality would also be beneficial for certain contributors who are working in a very similar fashion as well. Some of the limitations that I see in this current work is definitely the sampling time. So if you noise an image, say for 4,000 steps, you would want to denoise those images for 4,000 steps just to get an image back. And that's not going to work out in an FL world. So there has been definitely a lot of interesting works from NVIDIA and other large tech companies to reduce the sampling time. And that's something that can definitely be looked at in the future work. And the next is the hardware limitation, considering it was just a graduate work and it didn't have a lot of computation, but it's definitely something to look as to how can you do things like model quantization, model pruning, so that you can really reduce the size of these model weights from just a 12-bit, which is something like an 8-bit value as well. And the future work that I see in this domain are that this work does not really actively look at the privacy concerns. So I think looking at things like differential privacy so that you can account for the traceability or accountability are truly, really exciting works you can look at. And also extending the work by including other data sets, looking at other modalities in it well, and also definitely thinking about it in a responsible AI sense of manner by looking at the fairness, bias, and interpretability of the model are really exciting works that can be done as part of the future work. And I think that's it for my talk. And any questions you have, please feel free to ask them away.
Super interesting area, and I also appreciate the way that you kind of laid it out there at the end in terms of interesting contributions that can be made through this work into Flower. I think you were saying it kind of it also implies some areas where Flower could be easier for doing this type of work if you're trying to change it basically, and then also more fundamentally about the topic you're looking at, where the future work really lies. So we have time for questions. I'm happy to take some. Let's do it in this new way. If you're in the attendees, you want to raise your hand, just do so. If anyone here in the panelists want to ask a question, also go for it. We have one from Javier. So Javier, ask your question.
Okay, yes. Well, I really enjoyed this talk. I have, yes, a couple of very standard, not super technical questions, but I'm curious because I haven't had a chance to read the paper. How many clients did you have in your experiment, and did you find it like really important to have less clients so they can have more data, for example? Because I'm not super familiar with diffusion models, but I suspect that having more data would be beneficial.
Sure, that's a really good question. And the goal was to have lots more clients. However, I had to start off with just 10 to 15 clients given the computation that I had, So it was something that was just started off with 10 clients. And given that the model size is also big, just to put things in perspective, if you want to train just one client, you would require almost 4 gigabytes of memory just during training. So that kind of indicates how large of a model it is. So if you want to even have 100 clients to train in parallel, you would have, this X amount of memory space.
Okay, and also I found interesting the part where you were saying that first you train your global model with a little bit of data on the server, and then you use a small portion of, I think it was this data, to send it to the clients. So all clients can have some kind of aligned data or aligned training procedure. I'm starting to see that being more and more common in other FL papers. So I was just curious to see if you have been thinking about, for example, not starting from a pre-trained model that you train on the server, but maybe starting from an ImageNet pre-trained model, and then say, okay, let me just personalize to Cypher or something like that. Did you consider doing something like this, or what you would expect to happen if you start from a super high capacity model, for example?
Definitely. I think transfer learning is something we thought about. I mean, although it wasn't implemented as part of this paper, it was something we did think, because training from scratch was not ideal. So like you suggested, starting off with a large pre-trained model and then just transferring the knowledge to a smaller model would have been definitely worked out. We did not actively experiment with that, but that's something that we can definitely look into.
Okay. And also, yes, one final question. Do you have to open source the code?
Yeah, so I have been talking to Nick about it, and I'm planning to open source it eventually, yeah. But it's something that I would be doing it. First, I'm going to start off with just open sourcing my code, and then kind of looking into ways I can open source some of these modules into Flower.
Okay, cool, great. Okay, thank you.
Sure, thanks.
Any other questions from the audience? I think I see one being typed in here. Let me just see. They're saying, you had I think a few slides ago. It says it seems to be implying a few slides ago there was this statistic about number of rounds. It takes like 11 hours for a round, and so the question they're asking is how many rounds would it take for the model to converge? That's what they're asking.
So this actually, when I went try to experiment with this, I did not wait for it to converge, because that's going to take a really long amount of time, especially considering I'm training from scratch. So it was trained for around 10 to 20 server rounds, and each of them lasting for say under 100 epochs. So this was the time that I could put into place, but I don't see it converging at this point. It had to be at least trained for several more server rounds and several more epochs, but something that I just stopped with was 10 to 20 server rounds.
I guess I'm not so familiar with the details of diffusion papers. What does a centralized diffusion model typically run? It's how many epochs does it normally use?
It's a lot. They usually train it for a large number of days, and given the computation they have, they kind of run things in just they divide the data sets and then they train it pretty fast as well. Yeah, I mean, although it does sound repetitive, I think the computation was the main reason that hindered me from running it all the way to see how it would look, so that I can compare it paper to paper with that of the seminal paper out there. But yeah, it was just trained for 10 to 20 just to see how things were running. Yep.
I know, it's super interesting. I mean, I guess they're just sort of trying to give that frame of reference for what the I guess you're taking an important first step, and it appears to be necessary adjacent steps before this could be done sort of like every day, for example. Great. Well, thank you so much for the talk. It's wonderful, wonderful stuff. And thank you for using
Thank you
Flower.
so
We're
much,
always
Nick.
excited for like new use cases.
Mhm.